I'm Jeff Groh, and this is Partial Differential Equations. I'd like to talk a little bit about the types of differential equations that we're going to be working with primarily in this course. Let's begin with the heat equation. As we've seen, this comes from the continuity equation, which represents conservation of mass and can be derived using the divergence theorem. In particular, if you set rho v to be minus a constant times the gradient of rho, these are the fluxes, the mass that is being transported in a particular direction. What direction is the mass transported? If we assume this equation holds, we assume that the mass is transported in the opposite of the direction of the gradient of the density. If the gradient points in the direction of the maximal increase in the accumulation of this density, then we're assuming that the mass is transported in the opposite of the direction, in the direction of greatest decrease in that density. Making this assumption, we have minus k divergence of the gradient of rho. And the divergence of the gradient is called the Laplacian. The divergence of the gradient is the Laplacian. As we've seen, the Laplacian of some function in rectangular coordinates is the sum of the second-order derivatives. It follows that if U is a heat density, that the heat should flow in the direction of the negative of the gradient of heat, in the direction of greatest heat to lowest heat, and therefore it should satisfy the heat equation. It is customary to put a square here to indicate that this is going to be a non-negative constant. You can see that a negative constant would have the heat flowing in the direction of maximal increase, which would be pretty strange for heat. But we can investigate those possibilities later. If we tend towards some kind of a steady state temperature, U infinity is the limit as t goes to infinity of U, then ut, the partial derivative with respect to time of U infinity, we expect to be 0, which implies the steady state heat will satisfy what is called Laplace's equation. Laplace's equation exactly applies in those steady state situations. We can start the heat equation with external sources. So we can have an arbitrary function of time and space added in as an external source of heat added to or subtracted from the system. In the limit, as t goes to infinity, if we approach some kind of a steady state, we achieve something that looks like this. And this is called Poissons Equation. The wave equation takes the form 1 over c squared second order partial derivative of u with respect to time equals the Laplacian of u. I would like to look at a derivation of this equation in the one-dimensional case. In one dimension, we have 1 over c squared utt equals uxx. We're going to assume that we have a string that is fixed at these two endpoints. And we're going to let u be the deviation of the string from equilibrium position. Then we're also going to assume that the string does not do something like this. We're not going to allow it to go back over itself like that. So we're going to eliminate these situations. What is more, we're going to assume that the string deviates by just a small amount. U is pretty close to 0. Our string is going to vibrate straight up and down, but not side to side at all. So we're not going to allow any lateral motion of little pieces of the string as it vibrates. In this case, let me blow the situation up a little bit. Here's our string. We're going to take a little segment at x and x plus delta x. We're going to have a little segment delta s and a little width delta x. At the ends of this little segment of string, there are going to be two tension vectors. Tension on the right and tension on the left. And that's going to be true at each little segment as we march across the string. They're going to have different angles, direction angles. This is going to be theta right, and if we were to make this go in the opposite direction, it would have a theta left. We'll take this theta left as our direction angle, but if we multiply by -1, it'll point the vector into the right direction. So that TR is the norm of TR times cosine theta right, sine theta right. And T on the left will be minus the norm of T left times cosine theta left, sine theta left. What are the forces acting on the little piece of string? Well, the total force is going to be the tension on the right plus the tension on the left. We're going to assume these are the only forces acting on the string at the moment. We won't consider any gravitational force or any other external forces acting on the string, like plucking the string or blowing a fan across the string, nothing like that. The total force is going to be mass times acceleration. The mass of this little piece is the density times the delta x. We're going to assume that regardless, as long as we fix that delta x, if that delta s changes, the density will decrease, but you'll still have the same mass on the same delta x, because we're only allowing the string to vibrate up and down, not side to side. So this is going to be the mass density being, say, kilograms per meter, and the little increment in x being meters, this gives you kilograms, times the acceleration, which is going to be utt. This will be the total force. Now that's going to be equal to what we have over here, and we're going to assume that when we add these two forces of tension together, that the x components exactly cancel out. So we'll assume that the norm t right cosine theta right is equal to the norm t left cosine theta left, so that when we add these, the x components exactly cancel. So we'll only have forces going up and down. We'll end up with the norm of the tension on the right times the sine theta on the right minus the norm tension on the left times the sine theta on the left. So far so good. Keep in mind we still have this equation that holds, which allows us to get rid of the norm of the tension on the left. minus the norm of the tension on the left is going to be the norm of the tension on the right, cosine theta right divided by cosine theta left, and we're still multiplying this by the sine of theta on the left. At this point, we can make some factorizations on that right-hand side. In particular, the norm of the tension on the right can be factored out, as can the cosine of theta on the right. When we do that, we have to divide by cosine of theta on the right here as well. We'll end up with tangent theta on the right minus, you can see that we have tangent theta on the left. Now, about the tangent of theta. If our little curve is like this, we have u as a function of x. The slope of the tangent line is the tangent of the direction angle. And that is equal to ux. So here's what we have. The norm of the tangent on the right times the cosine of theta on the right times ux evaluated at x plus delta x minus ux evaluated at x. At this point, we divide off the delta x and take the limit as delta x goes to 0. You can see then we'll have rho utt equals norm tr. Now, another thing, we said the deviations from flatness are small, which means to within first order, cosine theta r is going to be pretty close to 1, because this will be pretty close to 0. All that's left then is the second order partial derivative of u with respect to x. If we now combine by dividing this rho off, we'll have some constant over here, and this will yield the wave equation in one dimension. It's customary to call this constant c squared, and you can see that it has to be non-negative for physical reasons, and it will represent the speed of a wave traveling down the vibrating spring. The Schrodinger equation also has some interesting features. We'll have some potential, which will typically depend upon the spatial coordinates, times our wave function as well. Also on our lineup is the Helmholtz equation, which has the Laplacian of phi equal to minus lambda times phi. We'll see this come up in certain applications as well. And we'll also look at the inviscid Burger's equation just a little bit in this course. What's different about the inviscid Burger's equation is that it is nonlinear. We have a partial derivative of u multiplied by u. What does it mean for an equation to be linear? It must be expressible in the following form. Here we'll assume that we have a multi-index of order less than or equal to n. This multi-index will look something like this: I1, I2 through ik. And the sum of the ik's will be the order of the multi-index. We can have functions and then partial derivatives. Well, which partial derivative? We're allowing there to be multiple partial derivatives here, equaling some function like this. The salient point being that different derivatives or values of u, we're allowing the order to be 0, which just gives you the 0th derivative of u, which is u. We're allowing that to be multiplied by an arbitrary function, but we're not allowing u or its partial derivatives to be multiplied against each other. U and its partial derivatives must appear at most once in the numerator in separate terms of a sum. That's what it means to be linear. What is an initial condition? It's where when you replace t by 0, you get some specified function, u0 of x. How about boundary conditions? What is a boundary condition? It's where u, evaluated at the boundary of some region, is equal to some specified function, which I guess we can call u boundary of t and x. Our typical problem here will have both initial and boundary conditions. Linear problems have some special properties. In particular, they satisfy two superposition principles. First of all, if the linear problem is homogeneous, meaning on the right-hand side we have a function that is identically 0, and u1 through uk, if these are all solutions, then so is an arbitrary linear combination. So any arbitrary linear combination of solutions to a linear homogeneous partial differential equation will also be a solution. The proof here is very simple, and you saw the proof similar to this in a class in ordinary differential equations. So I'll let you prove the last part of this theorem. We'll denote the sum of the derivatives by L. So LU equals F1, LU equals F2, and so on. Suppose that all these differential equations are solved by u1, u2 through uk. Then it turns out the sum of these solves the partial differential equation with LU equals F1 plus F2 through Fk. So if you have multiple independent sources, you can solve each of these independently with maybe simpler solutions, and then you can find the solution of the more complicated forcing situation by just adding up the different particular solutions. Burger's equation, the inviscid Burger's equation, has what are called self-similar solutions. Or sometimes rarefaction waves. They might look something like this. How about x divided by t? I claim that's a solution to Burger's equation. We can check just by calculating the derivatives and verifying this. If we take the derivative with respect to t, we'll have negative x over t squared. U is x over t, and the derivative with respect to x is 1 over t. And so you clearly get 0. So this is a solution. If this is x and this is t, you can see that at different ratios, x to t, different constant ratios, you'll get this solution varying in value along these different rays as you go out. Different slopes, if you will give you different constant values for u, these different little rays. That's why this is called a rarefaction wave. You can go from some region of, say, low u to high u by just fanning, going through this fan. These are also sometimes called fan waves for obvious reasons. A point I'd like to make, though, is that linear combinations of these fan waves are not going to be solutions to Burger's equation. In particular, let's suppose that w is c times x over t, just a scalar multiple, certainly a linear combination of this 1. What does it take for this, a constant times x over t, to be a solution to Burger's equation? It's easy to check. We'll just plug it in. You can see that we get negative c x over t squared plus c x over t, and then when we take the derivative with respect to x, we get another factor of c times 1 over t. So if we take the x over t squared out and a c out, we'll end up with 1 minus c left over. And if that's equal to 0, there's only two values of c that will give you a solution. C equals 0 and c equals 1. So arbitrary linear combinations of solutions to Burger's equation do not end up giving you solutions to Burger's equation. That's because Burger's equation is not linear. You're multiplying a u times a derivative of u with respect to x. When that happens, you lose the superposition principle. I'd like now to focus on the 1D wave equation, which you'll recall is 1 over c squared utt equals uxx. And I'd like to approach the solution to the one-dimensional wave equation using a principle called separation of variables, or separability. Our function is separable if it can be separated into factors in the following way: into a function big T, which is a function of little t, and a function of big X, which is a function of little x. Let me first review some notation. We're going to assume the ordinary derivative of t with respect to t is denoted by t dot. Newton used dots to represent derivatives with respect to time, and we're going to do that here. Also, Newton denoted derivatives with respect to spatial variables by primes. So we're going to denote the ordinary derivative of big X with respect to the spatial variable little x as big X prime. It may seem implausible that we can find a solution of this form with the variables separated out, in a product in this way. But if we can find a solution in that form, that has to be the solution because of the existence uniqueness theory for partial differential equations. In particular, there's Cauchy's existence uniqueness theorem that applies to linear partial differential equations with analytic functions as coefficients. Since we have constants as coefficients, Cauchy's theorem will apply here. So if we can construct a solution, that'll be it. I'm going to use this following substitution notation. Tx is going to be equal to u. When we take this and plug it in here, we'll have 1 over c squared t dot dot x equals tx prime prime. Now, if we divide both sides of this equation by tx, you can see on the left-hand side the x's cancel out. On the right-hand side the t's cancel out. And we're left with this very simple equation, 1 over c squared t dot dot over t equals x prime prime over x. Now, the key element of the derivation applies next. The left-hand side function depends only on t, time. The right-hand side only depends upon x. So if this equation applies for all x and for all t, you can fix some x, and then for all t that equation has to apply, which means that the left-hand side will be equal to this constant. That means the left-hand side must be constant. The same is true on the right-hand side. If you fix t on the left, this has to be true for all x still on the right, which means x prime prime over x must be equal to that same constant for all x. So these will be constant. Both sides must be equal to a constant. Let's suppose that we have this situation where we have some constant lambda. We must also then have x prime prime over x equal to the same lambda. Now, by the principle of trichotomy, every real number is either positive, negative, or 0. There are 3 options for lambda. Lambda could be positive, negative, or 0. Let's see which is most appropriate for different boundary conditions. On a string, let's suppose that we put our coordinate system here at 0 and at L. We should assume for all time at 0 the displacement is 0. And for all time the displacement at L is also 0. The string is going to be fixed at both endpoints and just vary in between. So, how are we going to have these boundary conditions satisfied? And what do these boundary conditions tell us about the sign of lambda? If lambda is greater than 0, we'll set lambda to be, say, m squared, so that x prime prime is going to be m squared times x. What functions have second-order derivatives equal to a positive constant times itself? You might suppose that exponential functions would be good options. In particular, any function of the following form, c1 e to the mx plus c2 e to the minus mx, will in fact be a solution. But we have a problem here. We need to satisfy both of these boundary conditions. So 0 has to be x evaluated at 0. You can see that if u is equal to t times x, and u at any time evaluated at x equals 0 equals 0, this doesn't have to be 0, this will have to be, you'll have c1 plus c2 equals 0. But the same has to be true when you evaluate at L. We'll have c1 e to the ml plus c2 e to the minus ml. The first equation tells you that c2 equals minus c1. You can see then that factoring c1 out, we have here something that looks a lot like a hyperbolic sine. If we divide by 2 and multiply by 2, we'll have twice c1 times the hyperbolic sine of ml equals 0. The hyperbolic sine equals 0 only when the argument is 0, so this will only work provided m is 0, but we've assumed m is not 0. M is positive. Or L is 0, but we're assuming that the string has a positive length. Both of these are called out, so that implies then that C1 is 0, and hence C2 is also 0, and these together imply that U is identically 0. So the only solution in the case when the constant lambda is positive is when the string is not vibrating at all, which is not an interesting situation. There are two other parts of trichotomy to investigate, so let's look at those next. Let's look at the case when lambda equals 0 next. If lambda equals 0, then x prime prime over x equals 0, which implies that x prime prime is 0. That implies then that x is of the form ax plus b. It's linear. Now, it has to satisfy the boundary conditions. So x of 0 has to be 0, which means b is 0. So that means then that x can be no worse than a times x, but now we have to satisfy the other boundary condition, and L is not 0, so that implies then that a is 0. So again, we quickly see that x is identically 0, and that implies that u is identically 0 in the case that lambda equals 0. That leaves only one possibility by trichotomy. We must in fact have lambda is less than 0. So let's suppose lambda is minus m squared in this case. Here then x prime prime over x will be minus m squared, which implies then that x prime prime is minus m squared times x. So what functions have second order derivatives equal to negative a constant squared times themselves? How about x equals c1 cosine of mx plus c2 sine of mx? So x must have this form in this case. Again, we have to check the boundary conditions. If we plug in x equals 0, cosine of 0 is 1, we'll end up with c1 is 0. So this part is out. 0 has to be x evaluated at L as well. And since the first part is gone, we'll have c2 times the sine of ml. what does that tell us about ML? We'll assume that C2 is not 0 so that we don't get something trivial. But sine is only 0 when you plug in integer multiples of pi. We deduce, therefore, that m times L is n times pi, where n is an element of the set of integers. You can't use anything for m. L can be whatever length you'd like, but m can't just be some arbitrary number. It has to be of the form integer times pi divided by the length of the interval. So you can see m is n pi divided by L, n an element of the set of integers. That gives us x is some constant, which I'm going to denote as c with a subscript of n, times the sine of n pi over L times x. Aha! This then allows us to have half of our solution. What's left is to figure out what capital T, the function of time, is. Remember that 1 over c squared t dot dot over t is also equal to this minus m squared. What do we have in this case? T dot dot will be minus m squared c squared times t. This is very similar to the situation that we just encountered for x. You can see then that t will be of the form c1 cosine of mct plus c2 times the sine of mct. You can see then that u, which is t times x, must have the following form. X was just some constant times the sine of n pi over L x. M is n pi over L. We can combine this constant with these other two. Let's just name them a n cosine n pi c over L times t plus bn sine n pi c over L times t, all times the sine of n pi over L times x. Our solution must be of this form. In fact, this represents a family of solutions, a different solution for each n in the set of integers. Because of the superposition principle, an arbitrary sum of these must also be a solution. We can take u to be an arbitrary sum as n. Let's see, what happens if n is 0? If n is 0, we'll get nothing. So we can start at 1 and go to infinity. We'll have solutions of the form an cosine n pi c over L t plus bn sine n pi c over L t, all times the sine n pi over L x. The beautiful thing to recognize about this is that this is a double Fourier series. We've been studying this. This is a beautiful application of the theory that we've already developed. We still have to check how this can satisfy the initial condition, the initial data. So the initial boundary value problem for the wave equation in one dimension must have this form. we have the boundary conditions. For all time, at the left-hand boundary, this is 0 and this is L, we have no displacement, and the same is true for all time at the right-hand boundary. We can have any initial displacement and initial velocity. So the initial displacement is going to be u0 of x. And the initial velocity is going to be u0 dot of x. So these are the initial conditions. Our solution must have the form u is the sum, as n goes from 1 to infinity, of, let's say, an times the cosine of n pi c over lt plus bn sine of the same thing, all times the sine of n pi over lx. We've already accounted for the boundary conditions. What we need to do now is account for the initial conditions. The initial conditions will determine the constants an and bn in the following way. Suppose that we pick apart the initial data, the initial function, the initial displacements, as a Fourier series. We should be able to do that. But because the initial displacement must satisfy the boundary conditions, it has to be of the form, the sum as n goes from 1 to infinity, of dn times the sine of n pi over L times x. Whatever this initial displacement is, it can't have the cosines because we can't have displacement at either of the boundaries. We deduce then at time t equals 0, at time t equals 0, all of these terms go away. These will all be 1. The an's must equal the dn's, where the dn's are the Fourier coefficients of the initial data. We can calculate these easily enough. To calculate the dn's, these are just the coefficients of the projections of the initial data onto our Fourier basis. In this case, we're going to multiply these by the sine n pi over lx over the inner product of the sine n pi over lx times itself. We just need to calculate the denominator. The inner product of sine with itself, the inner product that we use, of course, is on the interval from 0 to L. So we'll have the sine squared, which of course requires the half angle identity. Because of the period, the second term will integrate to 0, leaving a value of L divided by 2. So if the denominator is L divided by 2, we'll multiply the numerator by 2 divided by L. It follows then that the dn's, also known as the an's in our other representation for the general solution u, are going to be 2 over L times the integral from 0 to L of the initial displacement times the sine of n pi over L x. So we can easily calculate these Fourier coefficients that are part of the solution, and we've accounted for the initial displacements. What we haven't accounted for are the initial velocities at each point along the curve, and those will be determined by the other coefficients. If u, again, is the sum, as n goes from 1 to infinity, of an cosine n pi c over lt plus bn sine n pi c over lt all times the sine of n pi over lx, then ut will be the sum as n goes from 1 to infinity. The only thing that changes is the derivative of cosine is negative sine. We have to multiply by the derivative of the inside. We'll have n pi c over L times minus an sine n pi c over Lt plus, we'll put that on the next line, plus bn cosine n pi c over Lt, where we've already factored out the n pi c over L here, all times the sine of n pi over Lx. Now, ut dot at x, the initial velocity, will be what you get when you plug in 0 for t. 0 for t cancels out the first term, and we end up with the sum, as n goes from 1 to infinity, of bn times this n pi c over L times the only thing left, the sine of n pi over L x. Which means whatever the Fourier coefficients are for u naught dot, the initial velocities, they must be equal to the Fourier coefficients on the right-hand side here. In other words, bn n pi c over L must be the inner product of u naught dot of x with the sine n pi over Lx over, again, the inner product of the sine with the sine, which we already know is L divided by 2. So we'll have this equal to 2 divided by L, the integral from 0 to L of u naught dot of x times the sine of n pi over Lx dx. You can see the L's will cancel off, but we'll have to divide the n pi c over. So we'll have 2 over n pi c, integral from 0 to L, u naught dot of x, sine n pi over Lx dx gives us the other Fourier coefficients. So we now have a general solution to the wave equation. The displacement u is going to be the sum, as n goes from 1 to infinity, of an cosine n pi c over Lt plus bn sine n pi c over Lt times the sine of n pi over Lx, where an comes from the initial data in the following way: 2 over L times the integral from 0 to L of the initial data u naught times the sine of n pi over Lx, and the other coefficients are 2 over n pi c times the integral from 0 to L of u naught dot of x times the sine of n pi over Lx. You can see how we get a Fourier series representation, a double one in some sense, because we have both sines on the x's and cosines and sines on t. we'll have two different coefficients. One of them is determined by the initial displacement, and the other one is determined by the initial velocity. Let's do an example, which I call the pizzicato pluck. Let's have the string initially displaced like this. We'll pull the string up at a spot and then let it go. Let's suppose this is 1, 1/10, and 1/10. So it's going off at a right degree angle initially. The initial displacement, let's suppose the initial velocity is 0 everywhere. We're just holding this up. The initial displacement is going to look like this straight line, y equals x, and then it's a straight line that slopes downward. It's going to intersect here at x equals 1, so we'll have a factor of 1 minus x, we just need to get the slope right. The slope is definitely going to be negative, but as you go over 9 units, you drop 1 unit. So if I put a 1/9 here, I'll have a negative 1/9 slope, 9 units bumped over this way, 1 unit down, 9 units over. And when x is equal to 1, we have a height of 0. So this should be the equation of this straight line right here. Now, what are the Fourier coefficients of this initial data? Because the initial velocity is 0, we expect all of the bn coefficients to be 0 for all n. We need to find the an coefficients. An, you'll remember, we're 2 over L. L is 1 in this case. The integral from 0 to L, L being 1, we have to integrate this thing, u0 of x, against our basis functions, sine of n pi over 1 x for each of these n's. I suggest that we let our computer algebra system solve these integrals for us, and then we'll just do the simulation, the animation, on the computer. Our coefficients were 2 times the integral, but the integral is in 2 pieces. First part, the function is x multiplied by the sine of n times pi times x divided by L, which is 1. In this case, on the first piece, we're only going to apply that integral between x equals 0 and x equals 1/10. Between 1/10 and 1, the function takes a slightly different form. The function is going to be 1/9 times 1 minus x, and of course that's between 1/10 and 1. Now, I would like to simplify this expression but I would also like to assume that n is an integer. And you can see then that we get 20/9, the sine of n pi over 10 all over n squared pi squared as our coefficients. Let's make our function u then. It's t comma x going to the sum, and we don't need to find the other Fourier coefficients because those are all 0. We're going to have some expression times the sine of n times pi times x, these are the coefficients that we multiply times the cosine of n times pi times c times t, but we haven't defined c, so I'm going to define c to be 1. Now, how many of these are we actually going to sum? Let's suppose we sum 10 of these to begin with. And then we need to plot. There we go. You can see with n equals 10, we get this weird bump. And you can see, however, what happens with our wave. It's going to bounce back and forth in the following way. Let's stop this. Let's improve the approximation by going to 20 instead. It's slightly sharper here on this pizzicato pluck. And we'll make it loop again, but you can see what happens as the wave bounces back and forth along the string. We'll make this, say, 40. Much better plot. We can make this go to 6 pi by b. Let's increase the number of frames. Oops, that's way too many. Let's increase the number of frames to 100. Or to 200 frames. So you can see the wave actually inverts when it hits the other side, and then comes back and inverts back again. N equals 1 is called the fundamental mode of the oscillation. If we just plot the fundamental mode here, all other values of n give you what are called overtones.